to lab 7. This lab is called the maze solver. In this lab, you're going to be writing the program mazesolve, and its goal is to solve a maze that's supplied to it on standard input. So the program you're writing doesn't have any command line arguments. The maze will be sent in on standard input, and the maze will be defined in the following format. First of all, the maze files are composed of words with no line dependencies. This means the line breaks can occur anywhere as long as all the words are in the same order and they specify the same values. So the first word of a maze should always be rows, followed by the number of rows in the maze. The next word should be cols, followed by the number of columns. After that, you can have any number of wall specifications, and this defines where the walls will be separating two cells. The format of the wall specification is the keyword wall, followed by two indexes. And the index is for a cell in the maze. A cell in row I, column J, is at index I times C plus J. So you can convert from an index to a row column, or from row column into an index. And the wall has the wall keyword and then the two indices of two cells where the wall is separating them. So here are some examples of mazes and the graphical representation of what the maze looks like. So for all the mazes, the entrance to the maze is going to be at index 0 or the upper left wall here, and the exit's always going to be the last cell of the maze. So if you're given a maze with 4 rows and 3 columns, it generates a maze with no walls in between. And it just has an entrance and an exit. When your maze solver is looking for a path, you can choose any valid path through the maze. So in this case, where there's no walls, there are multiple valid ways to get from the start to the end. In the second maze, you have a single path that hits every single cell in the maze to get from the start and the finish. It has lots of wall specifications. M3 has some dead-end paths that you have to account for. And M4 has 2 paths through the maze, and your solution can be either the upper path or the bottom path. Both are good. And then M5 is an example of a maze that does not have a valid path through it, in which case your program would wouldn't return any path information. So as you can see from M2, the walls can be specified in any order, and it doesn't matter what order the walls are supplied. And there is no line formatting, just word order. So all that matters for the maze specification is the order of the words, and the order that the walls come in does not matter. So the first thing you ought to do in your program is to read in the maze file from standard input and turn it into an internal graph. And this graph will probably have a main class that is made up of nodes, and each node will have an adjacency vector or set that'll specify which cells that cell can get to. After you set up the internal graph structure, you're going to use a recursive depth search algorithm to find a path through the maze from cell 0 to cell RC-1. After you find a valid path, you should output the same maze that you read in, and it can be the same, or you can switch up the order of the walls because the wall order doesn't matter. And after you print out what the maze is, you should print out the path keyword followed by the index of a cell. And the path should be in order from the starting cell to the final cell. And it specifies the path you can take through the maze to solve the maze. So here's some examples using the first 5 mazes on the solution. And as I mentioned before, you print out the maze. Following the maze, you print out the path through the maze, assuming there is a path to take. For M5, there is no valid path, so you only print out the maze again, and you have no path information. So the output of the maze does not have to be the exact same as the input. It just has to represent the same maze. If there are multiple paths through the maze, your program just needs to find one of them. It doesn't have to be the shortest, and if there is no path, then no path output should be specified. You don't have to worry about error checking your input files. The input is going to be correct. The input you're given is going to be correct. And there are two useful programs for testing and displaying mazes. The first is MazeGen, and you give it a value of rows and the number of columns, and it'll generate a random maze with the given specification. And then it'll spit out the walls in a random order. The second useful program is Maze PPM, and it'll take a maze on standard input with or without the path specification or the path's answer, and it'll turn that maze into a PPM file, which you can then display on the screen to see what the maze looks like. And since PPM files are large, you can pipe it to convert in order to convert it to a JPEG, which is smaller. And here's some examples of the calls you would make to get out a JPEG image of what the maze looks like. And then here's some examples of the JPEGs of the solutions for the first 5 mazes. The first one shows the path taken in blue through it. M2 shows every cell is on the path, and it highlights it blue. M3 shows the path taken through it, and M4 shows its path, and then M5 doesn't have a path, so there's no blue. And then the displaying of the mazes gets really cool when the mazes get large, because as you can see in this mess of a maze, you can see the blue path snake through from the start to the end. The last program is MS Checker, which is used to check the output of the maze solve program you write. It takes a non-set solved maze as the command line argument and the output of your maze solver on standard input. If your solution to the maze solve is correct, it simply returns. Otherwise, it will specify an error as to why yours is not correct. So for instance, the first error it shows is the rows of the solution does not match the rows of the input. Another possibility is a bad solution, empty path, yet there is a solution to the maze. And that means that there is a solution, but your maze solver didn't find it. And then another bad situation is if your output deletes some of the walls inadvertently, and it says bad maze, missing some of the original walls that were in the maze. So that's the lab. If you have any questions on depth first search, you can look at the lecture notes on how to implement depth first search. The easiest way for this lab is to use a graph with nodes, the nodes that have adjacency lists that specify the edges of the graph, and the depth first search is going to be a recursive algorithm that will search through to find a path from the first node to the last node. And then you can either start at the beginning and find your way to the end, keeping track of where you've been, or if you start from the end and look to find a way to the beginning, once you find the beginning, you can just print out as the recursive functions return. So there's different options on how you can go about printing out the maze once you find a path through it, or printing out the path once you find it. Are there any questions about this lab? Okay.